Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In the last lecture, we have looked into a very special kind of transition metal organometallic complexes. These are called sigma alkyl complexes. We have looked into these complexes in the perspective of a very important area, which is C H activation leading to C H functionalization. In the last lecture, we have also looked into two very good examples of sequence of reactions involving these transition metal sigma alkyl complexes that include C H activation as well as C H functionalization protocols, and with this these complexes have been used to produce methanol methyl chloride from methane, which is a highly inert molecule in a catalytic as well as stoichiometric fashion. We have also seen conversion of an alkane to alkane Bohrnick ester using this again C H activation and C H functionalization sequence in a catalytic, reduced selective and thermal fashion. So, what this method allows us is that they use value added chemicals from very inert alkanes which have very strong C H bonds. In this lecture, we are going to take up a bit more detail the various characterization techniques at present at disposal that are there to understand transition metal sigma alkyl complexes. So, in this class, we are going to talk about now what is important to note is that in the course of C H activation, where does sigma alkane complex occur and does it precede the oxygen addition step. So, the first question one asks is, where does transition metal sigma alkane complex form in C H activation sequence that give a transition metal sigma alkyl complex. So, please note that there are two different complexes over here. One is transition metal sigma alkane complex, the other one is transition metal sigma alkyl complex. Now, in this alkyl complex, what is interesting to note is that oxidative addition has occurred, whereas in the transition metal sigma alkane complex, the splitting of C H bond or activation of C H bond has not occurred, but weakening of C H bond has occurred. So, transition metal alkane complex is akin to or maybe a variant of agostic type interaction that we had earlier encountered. So, based on these two complexes, then the question comes that where transition metal sigma alkane complex occur in the course of C H activation that give a transition metal sigma alkyl complex. So, does it occur, does it precede the oxidation addition step? complex precede the oxidative addition step and what electronic properties of metal and the alkane promote the oxidative addition step. Now, before we go in details trying to look at this, I would like to note that we have discussed some aspect of the properties of the requirement as far as the metal is concerned. What we had seen in the earlier discussion that for the CH activation to proceed, that the metal has to be sterically as well as electronically unsaturated, and that the metal also has to be electron rich so as to undergo the oxidative addition steps. We had mentioned this with regard to formation of various transition metal sigma alkane complexes in our previous discussion. Now, if one were to look at all these three questions as to where the transition metal alkane reside in the trajectory of transition metal alkyl complex which is formed after oxidation addition, what are the requirements of the metal as well as the alkane for it to undergo oxidative addition reaction. So, one can sort of conceive of this CH activation or formation of transition metal alkyl complex proceeding via following two reaction. For example, a metal Z plus cation reacting with methane to give this metal Z plus interacting with CH bond of methane. So, this leads to the formation of Tm alkane complex, Tm sigma alkane complex, which then undergo oxidative addition to give the following transition metal alkyl complex. Here the CH activation of this hydrogen and carbon has occurred as we have seen in other cases. So, this complex formed over here is a transition metal sigma alkyl complex. The difference between that, over here it is a alkane complex and over here it is a alkyl complex, and alkyl complex is formed after the alkane complex has undergone oxidative addition. After this alkane complex has undergone oxidative addition, that the transition metal alkyl complex is formed. Let us look in more details at this transition metal sigma alkyl complex. With regard to understanding as to how does alkane interact with transition metal. So, let us take a look at transition metal sigma alkane complex in bit more details. It is interesting to note that alkane has different binding modes to transition metal. Transition metal sigma bond energy is very weak, not very strong. For example, the transition metal sigma alkane bond energy is around 60 kilojoules per mole, which would be slightly higher than a hydrogen bond. Stronger. So, what it shows that alkane binds very loosely to transition metal. Not only that, the binding of alkane to transition metal occur via different modes. At least 5 different modes have been observed. For example, it can bind in a linear fashion, and this is described as eta 1 binding. It can bind by interaction with 2 different hydrogens of an alkane. This is defined as eta 2 H H, HH because 2 different hydrogens are involved. Metal can also interact with 3 different hydrogens of alkane. So, this molecule just flipped over. Similar to something like that, and this is represented as eta 3 H H H type of binding. These are all non-classical kind of binding. It can also bind to a sigma bond. And this is written as eta 2 C M binding, and lastly this can bind in a fashion shown here, and this is called agostic interaction. Now, if one were to look at it, one can see that all of this is intermolecular binding, whereas this agostic one is intramolecular. That is kind of very interesting an observation. So, what it shows is that alkane or CH of an alkane can bind in several ways in which the metal would interact with the hydrogen atom. It can interact with more than one hydrogen atom up to 3, and also it can interact in a intermolecular as well as intramolecular fashion. When it is interacting in a intramolecular fashion, it is called agostic interaction. Also, all of these interactions will at most weaken the CH bond, but never cleave it, will weaken the CH bond, but not cleave it. Cleave a CH bond, and that can be characterized by various spectroscopic techniques, as we had seen in case of agostic interaction. So, these sort of summarizes the various binding modes by which a alkane can bind to a transition metal. The alkane binding in solution has been characterized by UV visible spectroscopy, for example, this chromium hexacarbonyl, which shows lambda max at 229 and 280 nanometer, forms the alkane complex with methane at very low temperature in light, giving CO5 Cr methane, which shows a distinct lambda max at 489 nanometer. The same complex in C6H12 at 300 Kelvin in presence of light in laser flash gives the corresponding alkane complex that display a lambda max at 503 nanometer. Apart from UVVs, the transition metal alkane complex can also be characterized by NMR, proton NMR, for example, this Cp rhenium tricarbonyl compound in low temperature in presence of light at minus 80 degree centigrade, in presence of C5H10, eliminates the carbonyl to give the corresponding C5H10 complex, which shows this kind of CH sigma interacting with the metal. Now, which shows, and this has been characterized by eta 2 CH kind of binding. As this is very low energy interaction, they undergo various exchange processes and can also be seen to interact with other modes of binding. For example, of this type, which is eta 2 H H, and that can also undergo exchange to show a binding something like of this type, which also is a eta 2 CH. So, what we see that these alkane transition metal bond being very weak undergoes various exchange processes in the type of binding. It can start with eta 2 CH, end up in eta 2 HH, and then finally go back to eta 2 CH, and they would exchange very rapidly, that in NMR time scale the binding looks equivalent. Appear equivalent in so let me explain, means that for binding of this type eta 2 CH and eta 2 CH, these are unsymmetrical. As a result, there are two different kind of proton over here, whereas for eta 2 HH this is unsymmetrical binding, whereas this is a symmetrical binding. And a symmetrical binding would predict a single proton resonance for the two hydrogens, whereas the unsymmetrical binding would predict two different resonance for these two hydrogens. But as this exchange is very rapid, only one set of resonances appear in the NMR time scale. What is important over here is that various modes of binding can be picked up using proton NMR, particularly by looking at the chemical shift of the proton resonance. Structural characterization of alkane complex has also been achieved using X-ray diffraction studies. And this has been achieved for the heavier analog SiHe4. For example, for this molybdenum complex, which reacts with SiH4, giving this molybdenum PET2 complex. That binds with SiH4 to give this silane complex, and that finally equilibrates and undergoes oxidative addition to give the correspondingly silyl hydride complex. Now, these silane complex have been structurally characterized as has been said that because of this interaction the silicon hydrogen distance would increase, because this interaction weakens the alkane CH bond. So, D SiH bond length is 177 picometer, and this is eta 2 type of binding, whereas in free silane this bond is about 142 picometer. So, what is becoming clear that these transition metal sigma alkane complex can be characterized by various techniques including UV, NMR, X-ray, and all these complexes had the prominent signature that this transition metal sigma alkyl complexes has weakened CH or SH bond. As a result, they have longer SH bonds or they have weaker stretching frequencies which can be picked up by various spectroscopic techniques. We have discussed in this lecture is how an alkane transition metal complexes are formed, in what part of the trajectory of an CH activation followed by CH functionalization does this transition alkane complexes exist, what are their nature, what are their binding modes when they interact with the metal, how many metals can these, how many hydrogens can these alkanes interact with simultaneously with the metal, and what has been observed that it can interact with the metal all the way from 1 hydrogen to 3 hydrogens. And lastly, we have looked into structural characterization of these complexes, where we found structurally characterized transition metal alkane complex has a longer bond length than that of the free alkane for the silicon analog that has been structurally characterized. With this, we looked into various transition metal alkane complexes and various characterization method that are available, and in the next lecture we are going to take up something more interesting as to provide a comparison of alkane activation with regard to silane activation, with regard to dihydrogen activations, what are the molecular level interactions that occur between these interaction between the ligand entity and the metal, is there a commonality that exists between alkane activation, dihydrogen activation, silyl hydrogen activation. So, all these and more, lot more will be taken up in the next lecture, and I look forward to being with you to discuss this in more detail. Till then, thank you.